it is very exciting moment. So we have our final keynote session for SCA 2022. Wow, this is the easiest introduction for me to do, because if you attend the banquet last night, so you know who Daniel is, right? Daniel is our the recipient of the Early Career Award to highlight his great contribution to the community over the last few years. And well, I will go to the formal introduction. So Daniel is currently a principal animation programmer at Epic Games. And before that, he worked at Ubisoft to develop patterns like using machine learning in various areas of video game development, such as animation and physics. So he completed his PhD at the University of Edinburgh in 2017, with a focus on using neural networks and machine learning for character animation. He also has a number of applications of conferences like SIGGRAPH, SIGGRAPH Asia. So the talk for today is future animation systems. So yeah.
All right, thanks a lot. Yeah, thanks for inviting me as well. Like I said, SCA was also my first conference, so I have many fond memories. Today I'm going to talk about future animation systems, and more specifically, what lessons can we learn from rendering? Because I think we can all agree rendering in games is pretty incredible now. And there's many interesting things we can learn about the way that is developed. Yeah, I recently joined Epic Games. I joined in January. So a lot of the research I'm going to show you here, almost all of it is work I did before at Ubisoft and also previously at Edinburgh University. So if you guys haven't seen it, should really check out this latest demo from Unreal Engine, which is called The Matrix Awakens. And when I first saw this demo, it completely blew my mind. Like, the graphics are absolutely incredible, the fidelity and the detail and the lighting and everything. It felt like a real step up in terms of the virtual worlds we can inhabit. And also this world is huge. It's like kind of like a super New York, Manhattan Island sort of thing. And you can drive around, and yeah, it's just really, really an incredibly impressive demo. And so it's using this new technology called nanite, which, for those of you who don't know, it's basically this sort of really tiny, you can render these really tiny polygons really extremely efficiently. So here, there's something I literally probably never thought I would ever see in my lifetime, which is a game rendering every single link on a bike chain individually with individual polygons. And you can even see here, you know, the tread of the tire is actually geometrically modeled and being rendered. So this is like completely mind-blowing for me. So you can also walk around as a character in this world. So here's me going in and trying to like break it and make it do janky things. So here I'm sort of spinning the stick around and getting this character to swirl on the spot. So here's me trying to get this NPC to do weird things by getting in its way. So you can see just this sort of weird flip around backwards. This is what happens if you walk into a bollard or something. So the character just kind of goes like that. And this is like the dreaded invisible wall, which we still have in video games now, believe it or not. And the thing is, these guys actually did a fantastic job of this locomotion system. So it wasn't easy to find these little bugs and problems, but we're so far off having like the equivalent of every single link in the bike chain like rendered perfectly. Like the gulf is just completely vast in comparison to that sort of level of detail and attention to detail in animation. So my kind of hypothesis is that right now we're kind of stuck in the days of traditional rendering and all of this sort of thing you used to see before. And we need to get to kind of physically based rendering, which was a big revolution in rendering and changed a whole bunch of things. And lots of things changed between these two, you know, approaches to doing rendering. But two of the things I think are really important and I want to talk about today are what I'm calling fixing bugs in our understanding and a switch from direct control to indirect control. So I'm going to talk about those two and give some different examples. So bugs in our understanding. here's an example from rendering. It's something called gamma correction. So the basic idea is that when we have a monitor, it renders colors in this compressed space. So it gives more fidelity to dark colors because we perceive dark colors more than we do light colors. We perceive the difference in them. And up until about 2007, many games didn't account for this fact at all. And what this actually meant is that all the lighting calculations were wrong because they weren't accounting for this fact that when you're authoring a texture, you're actually doing it in this compressed space rather than in this linear space. And the fix is 2 lines of code. When you sample from a texture, you convert from the compressed space to the linear space. And when you output a pixel to the screen, you convert from the linear space to the compressed space. So kind of the lesson here is that 2 lines of code can make a huge change to everything, way more than features developed by whole teams. It's just a very fine detail. And actually, this bug is still not fixed. So there's still people even today. This is a well-known graphics programmer who's still like tackling these issues, which we've had going all the way back. And that's kind of like a really classic example. But if you look at what rendering programmers are doing today, they're still doing the same process. So here's a blog post from another well-known graphics programmer, and he's doing all of this complicated mathematics. And in the end, it's a pretty small change in this equation. So we go from this at the top to this at the top. So he's basically going into a lot of detail to work out what was wrong and trying to fix it. So it's something I kind of tried to emulate a bit on my blog. So here's me like showing that we can do integrals too as animation programmers. It's not just rendering guys. But I think this is something anyone can do who's interested in this area, is kind of go and try and drill down on these little details. And another example is I took the time to try and rederive some of these spring equations which we use for modeling PD controllers. And at the time, I just kind of did it for my own curiosity and fun. But since then, it's kind of revealed a lot of new insights and interesting applications, which we can apply to lots of different areas in animation programming. So for me, it was a really great practice to go back and do this and look at these fine details right from kind of almost first principles. Yeah, so this is kind of a big takeaway, which I think everyone in graphics is totally in agreement with, which is that these very small changes can be super important, and they can look like not much, like just a couple of symbols or a couple of lines of code, but they can make a much bigger difference than huge features developed by whole teams. And I think another really important point is you need to have an understanding of the whole pipeline. So if you don't know about how monitors work, you can't fix gamma correction. Okay, so you need to know, if we're talking about animation, maybe you need to know how a gamepad is working and how you're getting the inputs from a gamepad, and you need to know how these are getting transformed to a variable which is going to go to the animation system. How does the animation system actually render a pose, board kinematics, skinning, all of these different details. You need to have a good grasp of all of these, otherwise you don't have a chance of fixing these issues. So the second thing I want to talk about is direct versus indirect control. So here's another example from rendering. So historically, we had these things called specular maps, and they're they're like how shiny is the object, okay? And at some point, artists realized that if you have a metal surface, this shiny reflection, this highlight, it should be the same color as the metal. So if you have brass or something, it's going to be sort of orangey. And if it's plastic or any other material, wood or something, it's just going to be white. So what this means is that you want to have this color in your specular map to do the highlight. So this is like the direct control solution to this problem, which is we say we're going to let artists author colored specular maps. That may sound very simple and straightforward, but you might have built your whole pipeline up assuming that, okay, we put the specular channel in the alpha channel of the texture, or we do some compression because we know it's going to be black and white, or you might have a whole bunch of assumptions built up on this fact. It might be a huge change to your pipeline to allow this. And the indirect control method, which is what they use in physically based rendering, is instead the artists provide a metalness map. So they just say which parts are metal, and the rendering, the rendering system is going to look at that and decide what color to make the highlight, basically. So the problem with direct control most of the time is, one, we have some sort of fundamentally incorrect assumption. So in this case, the incorrect assumption is that specular highlights have a color. Okay, so they don't actually have a color. This specular highlight, it's actually just the blurred reflection of the light source. So once we move to a physically based rendering view of the world, we actually can realize that this isn't a sort of special highlight we sort of paint onto the object. This is just kind of the sun blurred or whatever. It's a light just blurred. And then we realize that this is not a highlight and this is not something to be colored. Secondly, this isn't actually what the artists want. They didn't want to be able to make colored specular maps. They just wanted the metals to be rendered more realistically, right? And have the correct colored highlights or reflections. So we can think a bit about a parallel in animation. So for me, it would be something like animation layering. So something we might have in a game is we have a character, want them to be able to run around and aim a weapon while they're running around. And so animators might say, okay, one way we could do this is we layer the animation. So we're going to have a different animation playing on the top half of the character. So if you're working in game dev, this is what might happen. They might come to you and ask, oh, can we have this feature where we can have different layers of animation? And this is kind of the same direct control solution we saw before. The indirect control solution is something more along the lines of they provide a set of aiming animations showing what style of aiming they want, and at runtime they give an aiming direction, and somehow the animation is inferred or produced, just like how in rendering we worked out what color to make this specular reflection. So again, we have some fundamentally incorrect assumptions here. So the first is that like you can separate animation into top and lower body parts. I mean, you can't. We all know it influences both. What you're doing on top influences your feet, and obviously vice versa. So if you do this, this creates what I call tank mode. So here's like a little animation setup I made in Unreal, and we can see how the top half of the character is like rotating around like the turret of a tank or whatever. And this is some guys pretending to do this in real life. So we have exactly the same problem as before, which is that we're not actually doing what the animators wanted. They didn't want the ability to layer animations. They just wanted to have their character aiming towards a target, right? So they've come to you with a request for something which is not actually what they wanted in the first place, and it could complicate the pipeline and make things very difficult. I think another interesting parallel for traditional rendering and animation is this idea of a shader graph. So this was a big part of how people built rendering systems in traditional rendering, which was you had a shader graph, or you had a bunch of custom shaders, or a shader artist, or a material graph, some sort of tool for building up some sort of complex system of how this surface is going to be rendered. And typically, if it's a visual scripting language, it's going to look like some sort of crazy, insane mess like this. So here's a little shader I made when I was like trying to be a graphics programmer for this metal cannon. And I thought it looked pretty good, right? Because I was doing some different things like, okay, when we're at like a glancing angle, I'm going to blend in a bit more the environment map, and I'm going to, adjust the color a little bit and do this and that. And I made up a bunch of different things just to sort of try and make it look good. But the problem was all of these things I just made up, like they have no connection to reality. They have no connection to how light works. They're just something I kept iterating on. The bar was like, does it look good enough to me? And I think we have a very similar parallel in animation. So when we're building these animation systems, in particular from blend from blend trees and state machines. We're building up this model of how humans move, which doesn't actually have any connection to reality. So, when humans are walking around, they don't like transition from an idle state to a sort of walking state and then transition to a turning state. We don't have this same sort of, this model is something we make up for our own convenience. It's not actually a reflection of how humans move. So one thing that changed for physically based rendering was that we started to see people build these dedicated systems. So for example, we'd have like a dedicated sky rendering system, dedicated water rendering system, hair rendering, foliage, and people would build these very, very specific systems. And in a sense, the shaders are still there, but they're kind of hidden away, and they're written by graphics programmers who studied this particular phenomenon and worked out exactly what the best equations to use are, or what sort of approximations they can use. And this is the interface you get if you use these tools like Unreal Engine or something. You have the sort of C system, and maybe you can change the color and some other sort of properties, but you're not really going to dig down and start editing the raw shader yourself. So this is something I think could potentially work for animations too. So maybe one way we can think about raising the bar is by looking at building these dedicated systems for very specific things and trying to hit a very high quality bar and use expertise and have users interact with these in ways that make sense and let them achieve what they want to do. One sort of interesting difference for animation is that we need all these systems to work together well. So it's very rare in a game that you like put a tree under the water and are like judging whether that's looking correct anymore, or you have some hair intertangled with foliage or something and you're like, oh, that's not rendered right. So they have this nice ability to separate these systems. In animation, we have to find a way to make them all work together. So on direct versus indirect control, I think one interesting thing is that the solution is usually obvious in hindsight, or at least it seems it. Like this idea of having a metalness map, it kind of makes perfect sense to do this once you've already seen the solution. But at the time, you always feel like the kind of next iteration would just to do the direct thing. So let's just have colored specular maps. Second thing is that accurate description of data is usually a good complement for indirect control. So what I mean is when we have the metalness map, what we're actually making is an accurate description of our texture and adding some sort of meta information or extra information. And that's what we're providing, rather than trying to directly control what the system produces or say exactly what color we want the highlight to be or whatever. And also artists, they don't always like indirect control, even when it improves realism and makes things easier for them. So for sure, making this metalness map should be easier than the colored specular map. That doesn't mean they're going to like it, and doesn't mean they're going to enjoy having working with these systems compared to doing things more directly. So that's kind of some things that I think are similar between animation and rendering, and maybe we can learn from. What makes animation different? So I think there's three kind of really unique challenges to animation. The first is that we're fundamentally dealing with dynamics and things that move, and rendering is almost entirely static things, static renderings of the scene. So that is a core concept we have to grapple with. There's also a really long history of gameplay and animation being linked. So we can go all the way back to like Mario and Sonic. And basically in these games, animation and movement is the game, So that's really a fundamental component of video games. Moving is often the game or a big part of the game. And seeing animation, seeing what the character is doing is a big part of the game. In a way, rendering might not be. And finally, we never reproduce exactly what we capture. So outside of a cinematic, we can capture some animation data, but the character always needs to be doing something slightly different, maybe going in a slightly different direction or a slightly different speed. And so we always have to adjust things. Compared to in rendering, maybe you have a rock object and it just kind of sits there, and maybe it's photogrammetry, so it's captured from the real world. and you don't need to do anything with it once it's there. We also have some advantages. So we have pretty good motion capture, and we've had this around for a long time, a lot longer than rendering. People have had photogrammetry and other ways of scanning material properties. So we have this really, really mature solution for capturing the real world. I think that's a very concrete base we can use when we're trying to think about, almost what are the equations or what are like the fundamentals of realism in animation. Well, we can capture exactly something that is very, very real. We also don't have to use specialized hardware, so we can do most of our processing on the CPU, and we have less data. So the amount of memory used by a texture is so much more than a pose of the character or whatever. And if we want to do real physics simulation for rendering, we're basically talking about path tracing or something like that, which is way too expensive to do in real time. But we have physics simulators which can get pretty good results in real time. So we can also lean on that. So I think these are three like fundamental advantages we have over rendering, which we should be able to exploit. So that's kind of what a lot of my previous research has been doing. So on the motion capture side, we did some research on using deep learning for generating character animation. And a big part of this was using these large databases of motion capture data. So here, for example, you can draw some paths along the ground and generate animation of these characters following these paths. And this is something you can do from the raw motion capture data. And you can also use lots of the other powerful things you get from machine learning and all these new developments. So for example, here we did some early experiments on neural style transfer. But I think a kind of more important point is that if we're building a system with motion capture data, there's some sort of built-in scalability to it. So I think one of the reasons this example of this guy walking over rough terrain was so compelling is that it's just super clear that building this sort of system manually and by hand and with little pieces of animation you structured together would just be so much work and just so much complexity baked into this sort of state machine setup that everyone could tell this was a different way of doing things and it could achieve different results. And for me, that's really about scalability and how can you grow the complexity of the animation you produce without growing the complexity of the system that produces it. So we can do this same thing with motion matching. So it's not unique to neural networks. It's more about having a data-driven system which you can drop a lot of data into and use. So here was some capture we did in the motion capture studio, trying to get a guy to run around and basically pretend he's like navigating rough terrain. See, we get all sorts of interesting sidestepping motions. And here's kind of roughly what it looks like when you take that data and put it in game. So again, immediately you can see there's so many fine details you can get now, which you couldn't get if you built this sort of system manually. So all sorts of weight shifting and little details to the foot placement. All of these things would just be so difficult to get if you built some sort of manual system out of different pieces. And I think the full body aspect to this animation adds a lot too, right? So the fact that we're getting the top half of the body complementing the bottom half, it adds a huge amount. Even little details like how he looks down at his feet where it's going. So for me, motion capture is about scalability. So if we can combine motion capture with data-driven systems, this sort of idea is if we want to have a character adapt to a different situation, we should be able to drop in motion capture for that appropriate situation and have the system know how to do it. And there's two kind of fundamental things, which is if we can make our system work with unstructured motion capture data, then it also helps the scalability because it limits the amount of processing time. And we need motion capture to be cheap in the first place. So I've worked in different places where the cost of getting motion capture was so vastly different. So when we were at the university, we would go and do our thing, and then we would clean it up if we wanted to, or we'd just chuck it out and recapture it or cut it up or whatever. It didn't really matter, but it was essentially kind of free. When you're working in the game studio, it can be very different setup. So the quality can be extremely high, but there could be lots of manual processes going on, lots of cleanup. It could be oriented towards capturing cinematics where you have expensive actors in the studio and you want to get their movements and what they did exactly right. And you don't want to throw it out and recapture it. Can't afford to do that. So there needs to be a cheap way to get motion capture for these things to be viable. And that doesn't necessarily mean like from video or something. That just means your processes need to be a good fit. So processing time. So when we have these small neural networks, or at least relatively small, then the performance can be pretty good. So this was our work, learn motion matching. And here our whole setup was about 200 microseconds per frame on average, which is about a kind of normal budget for a AAA characters animation. So usually I guess it's roughly between maybe 100 microseconds and 1 millisecond. And I think more interesting is that these machine learning controllers, they can act massively in terms of compression. So here's a data set we had with a dog that was captured in the studio. And when they built the conventional animation system with this, they took very, very small pieces of this data. But we could take the whole lot where the dog was running around randomly and not doing what it was meant to be doing. And we could just throw it all in. And you get all these little nuances and interesting details that you don't get if you just have very small pieces of data. So this is really cool, and it's really nice for these animals because you can use this unstructured data. So you can get these little straightening things. So here's another example. Here we captured about, I think we had about 30 styles of locomotion. Where we captured a little clip, maybe just 2 or 3 minutes of walking around and a little bit of turning. And we can put all of this into one neural network, and the weights of the neural network once it's trained are much smaller. So I think this links into what Rachel was saying nicely, which is that if we want to have virtual characters which actually have some personality and can convey their emotions, then one, animation is going to be extremely important. But two, we can have great hope that we can capture a lot of data and still use it realistically at real time. So we shouldn't be scared capturing big data sets with lots of emotion and variety and styles and different characters. We should try and use machine learning as much as we can with these things. Yeah, so essentially animation data, it's vastly smaller in size than what rendering people are used to. And this means we can process it pretty performantly. If we write more performant code, then we scale up better. So if you're interested in this, check out something called data-oriented design. But the basic idea is that, if we can have a game where we have 100 characters instead of 10 characters, we have a completely different game. So we have completely different options in what we can do and what we can produce. So for me, performance is a feature, and making something extremely optimized, it can completely unlock new worlds. It's not just about sort of machoism or I wrote faster code than you. It's actually a big feature and can be a big component of games. And machine learning seems like a really great tool for data compression. So if we want to achieve this variety we need, then we can definitely lean on it. So the final thing I want to talk about is physics. So there's a very long history of applying physics for character animation. This is just a few papers. So at Ubisoft, we found that lots of these papers, they tended to lack the sort of fast responsive control you need in games. So here's some previous methods, and you can see the arrow on the floor is the direction they want the character to be going in. And some of them are taking like 30 seconds to actually change direction. So the basic idea was that we would try and have a physics-based animation system track a real video game character as if it was being controlled by a gamepad. So the result is you get something like this, which is pretty nice. So this was some really fantastic work by Kevin, who was a student at La Forge, and Simon as well. So the problem we had with this was that we found that as we added more data to the system, the characters struggled to track it with the same robustness and the same quality as before. And in some cases, it couldn't track it, sorry. And our theory was that part of this was due to the use of reinforcement learning. So something you'll see a lot in these sorts of papers is a sort of mixture of expert style, where you split up the data set and you train individual reinforcement learning systems for certain parts. And you even see this in things like OpenAI training bots to do, StarCraft and Dota. What they actually have are individual experts which are specialized to certain behaviors. So I don't think this is something unique to animation either. So student Levi and Kevin again developed this great system called SuperTrack. And the basic idea was that we would train a differentiable system which modeled the physics simulator and use this and backpropagate through this to do our motion tracking. So with this system, we could handle these very, very large databases. So I think, again, this sort of reflects our intuition, which is lots of these supervised learning systems, they can be trained on billions of images or lines of text, and they don't seem to struggle with it at all as the system grows. And another nice thing is you can see the motion quality is really high, and this is because, at least I believe this is because when we have the gradients, we can go directly towards the goal and directly towards the pose, which minimizes the error. So we can sort of get a very, very precise tracking result. So these are some experiments we did comparing PPO and SuperTrack. So these plots are kind of the survival rate. So what this means is this is like the time axis, and this is like the number of characters still standing. So this is like after 1 minute, how many of the characters are still standing. And so we can see this is SuperTrack. We can track almost every animation for a long time. And there are some animations in this data set which can't be tracked, like one character pulling up the other character or someone getting pushed over in a weird way. And we can see that PPO pretty much completely fails on this database. So it does okay on some of the smaller databases, but on this large database, it basically completely fails. And another interesting thing is the generalization. So this green line is we trained our system on one database, and then we tested it on a different database, which it wasn't trained on. And although the performance is obviously worse, it does a pretty reasonable job compared to PPO, which again kind of completely fails to generalize at all. So it's kind of worth mentioning that we trained these two systems for an equal amount of time. And so lots of the PPO papers are training for a very, very long time, maybe a week or something. So it could be that if we trained for equal time, eventually the survival rate would be similar. So this was a kind of direct comparison in terms of training. So I think the kind of takeaway here is that it really is possible to physically simulate our characters, and we can get this level of realism in terms of contacts and interactions. But physics is also chaotic. So one of the big challenges in games is having a controllable way to use these physics systems. That's something I think is difficult to find. Okay, so just to conclude, I think when I was preparing this and reflecting, I could see that almost all my work was focused more on the advantages we had in this domain rather than the challenges, right? So I think this is always tempting to like exploit what we can to make great results rather than try and tackle our challenges head on. And I think it's really important to find a balance between the two, both as a community and individually. So I think it's interesting to think about back to some of the challenges I talked about and think, how can we tackle these actually? And for me, one really interesting challenge is this indirect control problem I talked about. So machine learning and physics-based animation, they both require this indirect control by definition. We can't directly specify what we want the character to do. But there's a whole bunch of different things that need to be satisfied for indirect control to be actually a good experience for users. So things like being able to specify fine details and adjustments, being able to predict what's going to happen when they tweak things, knowing what the result might be, having a fast feedback loop. So, having machine learning have this huge training time, that's not necessarily practical all the time. So we need to think about ways to make that easier. And ultimately, kind of the goal, I think, is that users should be able to create their vision in as little time as possible and as little pain as possible. And, it needs to be not just in a sort of kind of fixed user study kind of setup, but more as a general tool and a general philosophy to doing work. One other thing I think is important is that it's okay if indirect control is a learning process and it's not obvious at first. So one example is when Pixar switched to their path-based ray tracer, they sent their lighting artist on real film lighting courses. And so now, instead of playing with the lights and setting them to unrealistic parameters, they would actually put physical objects in the scene to bounce the light around in the way they wanted. And I thought this was cool because here's an example of someone doing this in like Unreal, using Lumen as well to light their character how they want. And the other thing you can do is you can adjust the material properties or adjust settings beyond physical bounds to create these kind of like cartoonish or supernatural looking things. Realism, I think personally, I think realism is a fantastic goal to aim for. And we have this problem in games, which is that the gameplay always needs to be sort of cartoony in a sense because it needs to be fun. So the character needs to be extremely responsive and needs to react, in a way that's pleasing. And we also might have very cartoonish actions like in fighting games and stuff like that. And I think, again, inspiration we can get from rendering is the fact that people like Pixar are making these stylized cartoonish films in physically based path traces under all of these real physical constraints. So personally, I think it's not a good excuse to say, let's not target realism because games don't require realism lots of the time. I think instead we need to find ways to allow artists to achieve their vision under these realistic conditions. And I guess probably my main point I want to make is I think it's really an awesome time to be doing character animation research. So there's so many interesting things we can work on. And we have this huge gap to rendering, but that's like a great challenge. And lots of people are starting to be really interested in investing in this and getting serious about fixing this. So I think if you're interested in having your research be practical and applied, this is like the perfect time to start getting into that. And yeah, I think machine learning and physics-based animation, we obviously see a lot of it at SCA. And it's because these are really fantastic advantages, but we also need to find balance with the challenges we have as well and try and make sure we tackle them head on. So that's everything. Thank you very much.
Questions? Oh, you can go first.
Again, thanks for talking. Really fantastic. So I have a one low level and one high level. The low level is regarding the moment. So everybody who tried this animation has been questioned on the concept of this study, right? So after spending many years solving this one, I found or I would be interested in your idea, whether it's more to do with the data, or capturing the data, or actually the physical model you use. Because my experience is a lot of the models, especially the ones we use in foundation, are in general simpler than a lot of models used in the state of their vision. Their capacity is actually smaller. So for a lot of models, I find that actually the quality of the generation actually is similar. So I started questioning whether that's the problem of the data itself instead of the method.
Yeah, I think it's a good point. And for me, I think the data is extremely important and the quality of the data. And it's something that, yeah, right now there isn't a data set available to the academic community, which is at the same quality bar which you see in the industry. That's for sure. And so I think getting that would be really fantastic for the community if there's a way to do it. I think it's not the only thing. So there's also attention to detail and making sure that all the code you're doing is clean and bug-free and doesn't have off-by-one frame errors and these sorts of things. That also makes a huge difference. But for me, the most important thing about motion animation quality is that you don't fool yourself into thinking things are working when they're not. And that's almost impossible when the data is low quality to really judge and do these comparisons. So essentially, you're like leaving yourself uninformed the lower quality your data is about what really is working and not working. Yeah, don't know if that answers your question.
Yes. Okay. My high level question. Think about animation. That is based the system, which is saying that we're beginning of the data to say this basic approach is that data driven is the showing that people are random. So do you think we have, or we are writing at the field of determination again? I mean, it seems that we are reaching the end of another cycle. We ran out a lot of people, but I think we still for kind of end of the cycle. Do you think there's more to do in this cycle, or actually
I feel like there's probably a little bit more, but I think the practical challenge right now is making sure these systems are reliable and easy enough to use for people, that they actually get some value added from them when they're implemented in their workflows. So I think in terms of like, model development and stuff, there's probably still are some really interesting things to be done. But I think just the practical challenges of deploying these is tough. So we already see the motion quality is so good at, recent SIGGRAPH papers. I'm sure if you did user studies comparing it to raw, high quality motion capture, some people wouldn't be able to tell the difference. So we're starting to get there, but making these things actually usable is still a huge challenge.
one last quick question. Are you looking to normalize the development models?
Well, I'm interested in lots of different things. Like I'm not a big believer in switching to new models just because they're new necessarily. So I've tried to make the models kind of simpler in my research when I can, but for sure they're really interesting approaches that they look very promising, and already we've seen some good results from them.
Thank you for your talk. Can you please explain a little bit about the process of transferring features from real data to the rendering system? I mean, so referring to your videos. So is it a process that you learn using a machine learning model, or is it using reinforcement learning, in which you're forming a policy from a set of policies? How does that work?
So what sort of features do you mean?
Yeah, for instance, you have like persons, real people walking, and then you transfer that to the rendering system to try to imitate those movements under certain conditions. that process, how does that process work?
So right now in games, it's most of it is still fairly straightforward kinematic animation using skeletons and skinning and kinematics. There are people experimenting with things like going via an animation rig or going via physically simulating character, but in general, it's still the normal sort of kinematic workflow. Maybe the only thing that's a bit of an exception, which is common in games, is there's usually lots of helper bones, which are used for like kit, like a a bag or something, which is like flapping on the side, or a cape or something. There can be a lot of additional bones which get added for lots of different little details and physics simulation and stuff. But yeah.
Yeah, thanks for the presentation. It was really cool, really nice results, and congratulations for the award. You mentioned data-driven or data-oriented design. So this is something I also do for myself, for my research. I don't big fan. So I wanted to ask you, like, do you have a practical example or a specific example? So some feature that you unlocked thanks to proper performance pipeline. And a follow-up question would be: did you face in your team or new colleagues some resistance against changing the workflow to more performance of the flow?
Yeah, it's a great question. I think one interesting example, which I thought was very compelling, was when we were building some of our R&D animation tech at Ubisoft. Tried to build it from the perspective of processing multiple characters at once. And when you batch multiple characters at once, you can get huge performance gains. And one example was the inverse kinematics system we built just for cleaning up our results. If we do inverse kinematics for all of our characters at once, it can be much faster than doing it, one by one, and a bunch of different stuff like that. And typically in lots of the games, they have very complex systems for turning on and off inverse kinematics for different characters based on how far away they are, all this sorts of stuff, because it can be expensive. And all of this code just managing who gets to do inverse kinematics and not can actually be slow in itself. So I think this was a good example of where actually just doing it in a data-oriented way, batching all our characters and processing them all together was faster than switching people on and off and deciding who gets to do it and who doesn't get to do it. And now everyone gets to do it as well. So this was like a huge gain. But yes, there's still a lot of resistance to this style of programming, even inside game dev and inside game engine teams. And a lot of it is about the architecture of historically how animation systems have been built. If you have a state machine and a blend tree, you have the kind of idea that every character is going to be following a different path of operations and in a sort of different state and doing very different things and not doing everything together. And so it might not make as much sense to build it in this data-oriented way compared to, say, we had demos showing 20 characters doing motion matching or something. And the fact that all these characters were doing exactly the same process meant that it was extremely efficient and much more efficient than having lots of different characters all at different points in this same machine. So I think that's another sort of interesting way in which these data-driven systems also complement the data-oriented design, in that we may have every character going through the same system, doing the same operations, maybe evaluating the same neural network, and we can get big performance boost from that.
Yeah, thanks for that.
Hello, it was a really nice talk. And my question is, human faces in animations are made more and more photorealistic. Then with a meta-human creator, it's a great improvement. Nevertheless, it is not that difficult to differentiate the created human face and the really like a real photo of human face. So in your opinion, what are the fundamental reasons?
For human faces, you mean? Yeah, I mean, I'm not really an expert in that domain. I think it's probably fundamentally coming down to the same things, which is this real attention to detail about all the very fine elements of, your rendering equations. And like we've seen at SCA, modeling the eye, for example, is a really brilliant example of paying the attention to detail to all these little areas. So that's at least my theory, but yeah, I'm not an expert in faces and rendering of faces and that sort of stuff.
Okay, thank you.
If we left the meeting.
I don't know, it's sort of really amazing talk. I have a sort of a long-term question, long-term thinking question about character animation. And so one idea I've heard discussed recently in the community is that having like equivalent of DALL-E for animation systems, especially natural language interface we can use to design animations. So do you think that that type of tool, if we could design it and engineer it, is the right type of tool in this context, like in the context of games, VR applications?
Yeah, it's a really good question. And I think it's a big debate internally in general about what the best way to approach this is. So one limitation of natural language is that it doesn't give you very precise control, so I can't say go and standard coordinate 2.543, whatever, exactly in some position, or maybe you can, but it makes it a little bit more difficult to be very formal about what you want the character to do. But it does seem to unlock a huge amount of creativity, and it's a very fun way to do things and control characters or images or whatever you're doing. So there's that aspect. The second aspect, I think, is, do you expect users to provide their own training data for the system? So DALL-E or something, it's essentially a pre-trained model, which you're going to give to people and say, use this, engineer the prompts to get what you want. If you can't get exactly what you want, it's kind of like tough. You can get as close as you can, and that's that. My personal hope is that if we can build systems where people can bring their own data, they will feel more in control and more understanding of what it's doing and why. But I could be wrong in that respect. Maybe the correct way to do it is for someone to get a huge database covering as vastly as much as they can, pre-train something and deliver that to people and say, don't worry about all the training and all those crazy details. That could well be a better way to do things. I don't know.
Thank you very much for the talk. Amazing talk. Thank you very much. From my research experience of character animations, as well as my limited experience on gaming, I find that actually interaction is a part where a lot of contexts are being delivered and where the fun of the game is being carried out. So people argue that Mario Bros is interesting because you can break the walls, you can hammer into everything, kill the turtle. So recently in SIGGRAPH, we start to see that there are more and more character animation paper that they start to have two characters fighting with each other, or maybe touching limited object, one or two objects sitting on a chair and so on. But it's still a bit far from having full freedoms of touching everything in different ways, pushing everybody in different parts of their body, in different forces, and being pushed by multiple people at the same time. So what do you think the challenge will be from one person to multiple people with a lot of objects?
Yeah, that's a great question. And I think one challenge is in the data, in that you have a sort of combinatorial explosion of data in lots of these cases, but you don't quite have the same in locomotion, for example.
Yeah.
So that's one problem, but I do believe that we should be able to get very large databases and use them with neural networks. So I would hope that can be solved. I think another problem is right now, most of the machine learning models we're working with, they have hand-designed features for their input, essentially, and you need to custom design it every time you have a different kind of interaction. So I think that's another big challenge where it'd be interesting to see how we can remove that part of it and have systems which can be generic for a whole bunch of different tasks, rather than be like specifically tailored to this or that.
And I also have follow-up questions regarding the data. Do you see a future of machine learning system on character animation that where we are less reliant on high quality data, that we can have even Wobbridge data from like poses captured from Keynote and still be able to generate good animations?
Maybe. My gut feeling is not really in that direction, because most of the really high quality systems we see built with machine learning are built with high quality data actually. And so there might be a way in which you can have a mixture of data quality. We've seen that as well at this conference. But fundamentally, I think it's a safer bet to bet on high quality data.
Yeah. Thank you.
And that was really, really interesting. I'm working on a project around photogrammetry and motion captures. I'm just wondering if you kind of follow up that question in terms of quality of data. Have you looked at using AI-based kind of single camera capture systems to generate mocap data, or are they just not kind of apply it?
It's been a little while since I've looked at them, but at least in the past, they can produce quite good results. But the fact is, if you have a very high quality optical motion capture system, your precision can be sub-millimeter. And if you treat your data properly and you have a good setup for processing it and all of that stuff, retargeting it, you can preserve that level of quality. And vision-based stuff, it's just very, very far from sub-millimeter. We're talking like centimeters and inches and stuff. So I think there's still kind of a long way to go there personally.
Are you guys using kind of exclusively accents in house to push captures opposed to
There's a variety, but I would say that for the highest quality capture, certainly my experience is optical motion capture is really impossible to beat, even compared to the inertial based one. So I would say there's a big difference.
One question is, what do you plan for this in the future? Like, you guys can kind of put it out into the world and let it run wild, or is it something that
Yeah, so for me, the interesting challenge is the indirect control thing I talked about. So that's kind of what I really want to focus on building, is ways to generate animation which are easy to control. So if we look at MetaHuman as an example, you can pull a MetaHuman into a scene and play with the sliders and get an extremely realistic character, better than what many AAA studios can produce just as a novice with some sliders. And right now, that the equivalent is not there for animation, not in Unreal or anywhere else. And that's kind of what I think is a really interesting target, is to try and have a system like that. You can drop a character into the scene. You can easily tell them what you want them to do, and the quality is going to be super high. So that's my personal research goal, at least.
Thank you so much.
Any further questions?
You said that motion capture, this is the way of scalability, but I want to know what's your point of view of handling a lot of different type of environment, like, because in video games you are subject to a lot of different environments, type of terrains. You can interact with a lot of objects, but if you just rely on local database, so the point of view is we have to capture it, or maybe we then take advantage of reinforcement learning on top of it to augment your database and stuff like this. Yeah.
Right, so we can never capture exactly the animation we want for exactly the context. Like I'm exactly here and I need to go and work on my laptop at exactly the right distance. We can't capture that for everything. So there will always be a requirement for procedural stuff, physics-based stuff, machine learning-based stuff. We can never just always be playing back the raw motion capture data. We always will need that. But for me, it's about having a grounding in reality. And like, let's say we do have an animation of me going to work on my laptop. How can we judge whether that's realistic? In rendering, we might have some equations we can use. We might have some ground truth from a path tracer. In animation, what we can have is motion capture, and we shouldn't be scared of using that as our grounding for what is realism and what is kind of like physically correct in some sense.
Thank you.
Any other questions? Well, I do have one question. So you show mostly you show some human motion capture data, and you also show one of the data set on dogs. So what about other animals? So because for other animals, some of them may be difficult to be captured, and you also mentioned that maybe we say that where we rely on high quality motion data. So would you mind sharing with us some of your experience, or what do you think about some other?
Yeah, I think it's a really interesting and challenging question. So I guess what I would say is, if you want to think about how to potentially deal with this, we can still look towards rendering, because it's not like rendering guys don't have to render aliens or weird creatures. That they still have to render them. They still have to work out what their materials are. Is it like a beetle shell or something? So they are also not free from this problem, and they also have ways to solve it, which is like taking inspiration from the real world, like taking a beetle shell material or taking a slime material or something, and combining them in interesting ways. So I think we can try and approach it the same way in animation. So we can use motion capture, we can use actors acting in specific ways, we can use retargeting, procedural animation, physics-based animation. We can use all of these things to take something from the real world and make something supernatural from it. And we shouldn't be scared of doing that in the same way that rendering people do that.
Any other questions? But don't worry, we will have a coffee break right after this one, so I think we can discuss it offline. So let's thank Daniel for the very inspiring talk again.
Thank you very much. We'll have a coffee break right now, and please come back around 2:30, if I remember correctly. The coffee will be served around in 5-10 minutes. Thank you.